How are you, my friend?
I'm very good.
You ready to go?
Yep.
All right, knock 'em dead. Have fun.
Okay. So, some of my favorite places in the world that I've been fortunate enough to visit are the Great Barrier Reef, the Outer Banks, and Alaska's glaciers. But unfortunately, global warming is killing all of these places, and climate change due to carbon emissions is real. So, did you know that about 700 million metric tons of CO2 are deposited in the atmosphere every year by the airline industry? And on top of that, high-altitude carbon emissions have about double the effect of ground-level CO2 emissions. We need to think outside of the box to increase aircraft efficiency. So some current solutions are NASA and MIT's shape-shifting wings, which increase airframe efficiency over wing flaps, but theirs use heavy actuators that go inside the fuselage because no one has been able to find a strong and light enough actuator that can fit inside of a wing to increase aircraft efficiency and increase wing shape flexibility. So my solution is in two phases. Phase one was the PAM actuator, which I did for my entry video, and phase two was the Bionic wing, which I did for my summer project. So this is the design for my original PAM actuator. You can see there's one polymer artificial muscle, which is fishing line coiled into a special shape, and then nichrome wire wrapped around it, and then when it's heated up, it contracts. And then I also use 3D printed parts and a spring. So I built a test model aircraft, and you can see there are actuators that I made and the sensors inside of the plane. And I did actual test flights with it, and I collected telemetry data from the sensors in flight. So I used that telemetry data and put it into equations and found the experimental coefficients of lift and drag. And I also found the theoretical coefficients of lift and drag in an XFLR software, and they both agreed. So what that told me is that aircraft efficiency may be optimized for different phases of flight using the PAM actuator. And the PAM actuator is scalable, strong, thin, light, and it's cost effective. But some major challenges I had with my original design was that it had slow activation and the wing shape was limited. Now, introducing the Bionic wing. So this is a picture of what it would look like in an actual aircraft. You can see there are multiple ribs, many ribs that each have multiple polymer artificial muscles, and they twist around a rod, and that allows for complex wing twisting patterns. So this is all the components of it, but the important parts are that it has a flex sensor, a 3D printed vent wheel, and two opposing muscles. So here you can see when the bottom muscle contracts, the wing end goes down, and vice versa. And also, when the top muscle contracts, the bottom vent opens, and that lets cool air in to cool the bottom muscle to allow for faster relaxation time and faster overall actuation time. So I used Arduino and various sensors to program the Bionic wing. And here's the layout of my design, and I 3D printed a vent wheel by myself. And I used 3M fluoropolymer film for my wing covering material and 3M Kapton tape for heat resistance. So here's a video of the Bionic wing actually working. You can see there the lights light up to signify which muscle is actuating, and you can see the vents at the top and bottom open and close when they twist around the vent wheel. So I did tests on actuation speed and temperature, but I found that the vents keep the muscles cooler and they increase the actuation speed. So some key benefits of my design is that it has higher efficiency and wing shape flexibility, and it's cost effective. And some short-term applications for this design is for many types of drones, such as agricultural drones, firefighting drones, search and rescue drones, and some long-term applications are for maybe even commercial aircraft someday. So here's a demonstration of an actuator that could be used in commercial aircrafts. It has 40 parallel muscles, and it weighs less than a baseball, but can lift more than my weight. So for future research and work, as I was saying, I can use it in drones and commercial aircrafts. And I also just want to say a big thank you to everyone listed here on this slide, especially my mentor, Sam. So an ending thought, In 1903, the Wright brothers built the first airplane that used twisting wings powered by their own human muscles. So if we think outside of the box, just like the Wright brothers did, we can increase aircraft efficiency and reduce climate change and make airplanes great again.
Thank you very much. Great presentation. I'm just curious in the design process, where you began. Did you begin with concept? Did you begin with model in mind? And whose ideas were you building on?
Well, I've always been interested in airplanes, and I saw an article about polymer artificial muscles, and naturally I thought about how I could use them in airplanes. And then when I heard about shape-shifting wings too, and how people needed a strong and light enough actuator that can go inside of a wing, I realized that polymer artificial muscles were just perfect.
Thank you.
Thank you so much. That was a great presentation. Can you tell me a little bit about some of the issues you faced or some of the roadblocks you faced along the way?
So the testing of my aircraft was very difficult because I had to test it multiple times, many times, to get it perfect and make sure that it flew correctly. And so I actually had a first prototype, and the second prototype is the one that you saw in the video. So the first prototype, it fell out of the sky and was smashed to bits. But so I had to keep working on it and make a more sturdy model, and I eventually used carbon fiber rods, and that helped with the process.
Thank you very much, Leo. I would love to hear about how your 3M mentor helped you throughout this process.
So he helped me with some technical stuff, but most importantly, he helped me to learn what it's like to be an actual scientist working at 3M, and he taught me like how I can actually work and put my ideas out there and be an actual scientist.
This is great work here. Could you explain in a little more detail how a polymer artificial muscle works?
So I don't know the exact material science of it, but it is fishing line, and then when you twist the ends in opposite directions, it naturally coils, and then you just heat it up and it contracts and has an extremely high strength-to-weight ratio.
Wonderful, Leo. What other tests would you need to complete your innovation?
The next steps, as I said, I'll put in drones in short term, and some other tests I can do is to try to manufacture them more consistently, and to try to improve the speed and find the perfect way to actuate them, because it's a very new technology and very little research has been done into it.
To build off of that, with it being such a new and innovative bit to aviation, can you talk a little bit about what you think the differences in safety of the Bionic wing compared to normal wings would be?
Yes. So in my original aircraft, I found that the muscles overheated often. So the vents actually help, and I have not experienced overheating at all. And the two-muscle design allows for much greater stability, and the wing can move in better directions and keep people safer in the air.
Leo, did you contact any experts in the area? Maybe some folks that are doing some research on flight or aeronautics or things like that? And if you did, what did you learn from those folks?
Yes, my mentor Sam actually connected me to some 3M scientists, Howard Creel and Larry Hebert, I think. But they knew a lot about flight and aircraft, so they helped me improve on my design and come up with some good ideas.
Leo, how did you measure, when you made your model and incorporated your idea in the model, how did you measure changes in efficiency of flight?
How did I measure changes the efficiency of flight. So what I really measured was that, what I wanted to figure out was that you can optimize efficiency for different phases of flight. And so you can increase the angle of attack of that outside rib and like twist the wing down kind of. And so that allows for more lift in takeoff, but then you can untwist it and return it to its original form for cruising. And that has much greater efficiency because it doesn't have the vortices that wing flaps do in traditional aircrafts.
So is it really more of a proof of concept than something that could actually be measured?
It is a proof of concept.
Nice job.
Thanks.
How you feeling? Good?
Yeah.
All right, we're going to have you go out this way. We are halfway there, so we've seen 5 of our finalists. We have 5 more to go. But for those of you that are watching online, those of us in the room, we are going to take a 5-minute break, and we'll be back with the second half of our Young Scientist finalist competition. See you soon.